Good afternoon. Hi, everyone. My name is Asta Lee, and I'm a founding software engineer at Aurora Innovation. I've been working on autonomous robots for the last 7 years, from unmanned aerial vehicles to satellites to self-driving cars. Today, I'm going to talk about how we take advantage of machine learning to integrate machine learning into our self-driving system. So Aurora's mission is to deliver the benefits of self-driving safely, quickly, and broadly. To do that, we're building a self-driving platform that powers all types of vehicles. We were founded in 2017 by 3 industry leaders: our CEO, Chris Urmson, who led Google's self-driving project; Sterling Anderson, who launched Tesla's Model X and Autopilot; and Drew Bagnell, who is a faculty member at Carnegie Mellon and worked in Uber's autonomous vehicles division. We test our vehicles in Palo Alto, San Francisco, and Pittsburgh, and we recently closed more than $600 million for our Series B, and Amazon was one of our investors. So we've been able to take advantage of machine learning and engineering to build a robust system that can handle all sorts of complex environments. This is where I get to show you some cool videos. So these images show our autonomy stack run on the Aurora vehicle you see in the scene. And this is real perception data. We've simply overlaid its outputs onto video taken from above. You'll see stable tracks come into view of all sorts of actors. And here are some more videos of intelligent behavior. On the video to the left, you can see us merging onto the freeway. In the middle, we navigate a left turn at an intersection. And on the right, we smoothly track a group of cyclists moving alongside us. And all of this is from live runs. This is code deployed directly on board our autonomous cars, the fleet that we're testing across the country today. So self-driving is one of the most interesting and most complex problems in robotics, and core to our technical approach to that problem is the idea of fueling the rockets. So there's this saying we often repeat at Aurora: don't try to build a ladder to the moon. And this is kind of a silly expression, and I know we have some real rocket scientists out here. But the idea is that building a ladder lets us get incrementally closer to the moon. Day by day, we can make some progress, and engineers like me really like the feeling of making direct progress towards a goal. But obviously, we'd never be able to get there by just building a ladder. So to actually get there, we have to build a rocket, which initially appears to make no progress and sits on the pad for a really long time. But once it's launched, crosses the 250,000 miles in just a matter of days. So at Aurora, we fuel those rockets. Our goal is to get autonomy out quickly. And to fuel the rockets, we invest in machine learning over manually tuned, hand-engineered rules. We invest in large-scale training pipelines. We invest in high-quality data pipelines and deterministic replay and cloud analysis tools. And this is because most of the work in machine learning is building that infrastructure and those pipelines. And that's where most of our efforts at Aurora are focused, to fuel that learning rocket ship. So we applied this technical approach throughout our self-driving system, which includes 2 core components: our perception system, which lets us understand the environment and other actors, and our decision-making system, which allows us to determine the course of action through that environment. To dive into more detail, perception is the process of observing the world through various sensors and analyzing this data to build a detailed model of the state of the world and the actors in it. And perception is really hard. I know because I work on it all the time. But 3 primary challenges in perception are managing the scene complexity that we find all over the urban sites where we test, and achieving extreme accuracy in our perception in those areas, and also managing the long tail of edge cases and unusual situations. So here's an example of a scene from San Francisco. The blue boxes represent vehicles that we're tracking around us. The gold boxes are cyclists. The red ones are pedestrians. And the black vehicle in the center is our autonomous car. All of this is overlaid onto raw LiDAR sensor data. So in a complex urban scene like this, Aurora has to achieve extreme perception accuracy in our predictions of the state of objects around us. And I'm talking about estimating the heading, the extents, the size and shape and category, the velocity, the yaw rate of an actor to centimeter level accuracy, even coming from 200 meters away. And we have to achieve this level of accuracy in all weather, through storms and snow and sleet, and also through occlusion. This problem is hard, even for a typical urban scene. But additionally, we have to manage the long tail of challenging, surprising, and unusual situations. We've seen some crazy stuff on the road. We see unicyclists and geese crossing the road. We see people dressed like traffic lights. And the long tail problem is really hard because machine learning is powered by data. And it's really difficult to get like 10,000 examples of a house stacked on a truck cruising down the freeway. So our approach to these challenges starts with our state-of-the-art sensing architecture. We use automotive-grade cameras, radar, and LiDAR to provide 360 coverage of our environment. So we believe that one day it might be possible to have vision-only self-driving. As a computer vision engineer, I can't wait for this day. But right now, multiple modalities enhance safety and reduce our time to market. We believe that perception is ultimately a matter of statistics, which means that we have to drive our error rate as low as possible, lower than what can be achieved with vision alone. We take advantage of the differences between sensors and utilize sensor fusion to maximize performance and recall. We combine sensors to achieve levels of accuracy that are orders of magnitude above and beyond what we can achieve with one sensor alone. So this slide demonstrates some example sensor failure modes. Cameras suffer at nighttime, and it's also hard to deal with situations with high dynamic range. Radar suffers from Doppler ambiguity, and especially in tunnels, we get multipath or ghost returns. And LiDAR has its own artifacts. We get returns off of snowflakes in a storm, as well as off of vehicle exhaust and water vapor. But by fusing data from all three modalities, we can combine strengths and overcome orthogonal failure modes. Only by combining the strengths of multiple sensors can we reach the high standard for perception accuracy that's required for safe driving. So over the last couple of decades, it's become increasingly obvious that there is no credible approach to perception that isn't deeply rooted in machine learning. There's just no way to hand-tune a set of rules that would allow you to pick out each individual pedestrian and vehicle on a busy, crowded street. But in order to power our machine learning systems, we use experts to build our data sets. And this applies to any large-scale machine learning problem. We build custom tools so that human annotators can provide high-quality labels. And we choose a label representation that is correlated both across modalities and across time. And we also have found through experience that label quality is much more important than quantity. So a smaller amount of high-quality labels lets us achieve better results than a large quantity of low-quality labels. But quantity is still important, so we build automated and scalable pipelines that let us label massive amounts of data. And yeah, so besides all of this, we actually really care about challenging and interesting data. But most of the time, driving is really boring, which is part of the reason why I work on self-driving cars. So to gather the really interesting data, we label around interventions, which is when the vehicle operator takes over from the autonomous system. Interventions are really good signal that we've just encountered a really unusual or challenging situation. So by labeling around interventions, we can get data that is more interesting than by sampling uniformly, for example. This is hard example mining in the real world. Although we need machine learning to power our perception approach, it's not enough. We have to refine machine learning with rigorous engineering. We consume machine learning components within an engineered framework that uses those learned outputs in a way that conforms to the nature of reality. So if you take a look at the video to your right, there's a dividing line. And on the bottom of the dividing line, we show raw bounding boxes that are the output of our machine learning detector alone. Machine learning is a great way to provide initial estimates and detections of objects and get a sense for what their state is. But on the top of the dividing line, you'll see our high-performance, multimodal, and multi-hypothesis tracking tremendously refine that performance and smooth over that initial estimate of where the objects are. And on the video to the left, you'll see how our engineered fit improvement smooths over and tightens those bounding boxes to reduce our nearest corner error for the vehicles around us. In addition to combining machine learning with within a rigorous engineering framework, we follow the strategy of strict accounting of all sensor returns. We call this no measurement left behind. What this means is we don't discount any sensor return without explanation, even if that explanation is that these LiDAR points are the result of exhaust from the vehicle ahead of us, as shown in the red circle in the image. And this is critical when deeply integrating machine learning, because although learning-based approaches can achieve outstanding performance on certain classes of objects and actors, they remain inevitably incomplete in their understanding of the world. So by carefully explaining all sensor returns, we can track and respond to unusual objects, even if we don't fully understand their precise state. This lets us handle the long tail problem safely. So once we generate a model of the world using perception, we then make decisions to navigate around and interact with those actors. Our planner is conceptually always generating multiple plans, multiple contingencies, and constraining the vehicle selection of actions to ensure that our behavior is good, both in terms of what we expect to happen and also in what might possibly happen. And the three primary challenges in decision-making are managing the complexity of multi-actor interaction, dealing with decisions that affect our environment, and guaranteeing safe, human-like operation even when something unexpected happens. This is a video taken in Pittsburgh. We are navigating a left-hand turn through a dense crowd of pedestrians. If you look statistically at how humans make decisions, you'll find the importance of context. Humans have a lot of patience for finding a gap when the intersection is not as crowded, but less patience on a busy road. So it's hard to build hand-tuned rules that would let a vehicle find a small gap through this dense crowd, but also wait patiently for a single pedestrian to walk by. Our environment affects our decisions, but our decisions also in turn affect our environment, both directly and indirectly, in that other actors respond to the decisions we make and how we behave, but our decisions also affect our future observations, which creates this dependency loop that is a challenge to reason about. And it's not only the effects that we have on other actors that's important, but also other agents' effects on each other. In this scene, you'll see an oncoming vehicle coming over into our lane. They're making some space for the cyclist as they pass, and we should be able to anticipate that they're going to shift into our lane, and then after they pass the cyclist, shift back into their own lane. So instead of treating this oncoming car as totally unpredictable and deeply non-compliant, we should simply slow down and make appropriate space for them. So in autonomous vehicle decision-making, we have to consider how actors interact with one another in addition to respond to our autonomous system. And of course, actors do all sorts of non-compliant things. On the video to the left, a cyclist cuts right in front of us. And on the video to the right, there's a pedestrian jaywalking across the street. Decision-making is inherently a difficult, multi-agent, game-theoretic problem, and the edge cases explode when we have to consider four-way stops and traffic lights and pedestrians, and then also actors interacting with one another. So how do we address these challenges? I'd like to walk you through a simple example of decision-making in the context of highway driving. We can start with a simple rule like follow the vehicle right ahead of us. We actually call this ACC, or adaptive cruise control. When we start making decisions, they're also pretty straightforward, like should we continue following the vehicle ahead or should we change lanes? Traditional approaches to decision-making tend to be grounded around a heavily manually engineered approach that attempts to specify decisions well in advance. So you can imagine being able to define a set of rules that inform which decision the AV should make, such as whether there is a vehicle within 20 meters in the target lane. But these rules don't scale to the complexity of urban environments and multi-actor decision-making. Manual tuning and engineered state machines just can't generate human-like behavior. Machine learning is key. So we learn statistical models that can accommodate uncertainty, including the uncertainty from an upstream perception system. And we constrain and validate these learned approaches using regression tests. All of our autonomy code has to pass a battery of simulated and real-world regression tests before we ever test on the road. In addition to this battery of tests, we guarantee that learned plans are safe using the idea of formal invariance, which is an old robotics idea that we've adapted from deep experience in the field. These are hard-coded descriptions of a desired system state. And an example is the close following invariant. We should make sure that we can always come to a safe stop and avoid collision with the vehicle ahead of us, even if they suddenly slam on their brakes. So we've designed a planner that will never violate one of these invariants. But sometimes other actors can cause an invariant to become violated. For example, if a vehicle comes in from beside us and cuts right in a way that we no longer maintain this safe following invariant, the system prioritizes returning to a safe and conservative state by slowing down until we once again are able to avoid collision. So in this way, we build learned models that are constrained by our safety requirements, and we learn plans that are, in this sense, correct by construction. Within the realm of safe, there are still an infinite number of decisions the planner could choose. So we layer in machine learning to achieve behavior that is natural, interpretable, and predictable to other drivers. We capture these discrete decision and continuous maneuver preferences from skilled drivers who implicitly demonstrate the subtleties of human driving, from how much lateral acceleration we should apply to how to infer which of the other drivers on the road is going to assert right of way. And we also learn when our vehicle operators provide constructive feedback through corrective action. These interventions provide learning through interaction with our self-driving system. So I've shown you examples of decision-making in the real world, but now I want to talk about learning from experts in a more theoretical context. And here's a toy problem to illustrate a naive approach for how we might learn to drive a car by imitation. The problem is that we have to pilot a car around a racetrack, and the speed is fixed, so all you have to do is steer the car. You get a camera image for input, and we want to learn a policy that, given this image, can output what angle to turn the wheel so that the car stays on the track. The supervised learning approach starts with expert trajectories. So we have human expert drivers drive the car around a track a few times, and this is easy because human drivers are actually pretty good at driving. And we can sample a data set, pairs of input images and output steering angles. And we use this data set to train a policy. But when we run this policy, the learned policy fails and the vehicle drives straight off the track. And this is because statistical learning assumptions break in sequential settings. In statistical learning, we assume that the data is IID, or independent and identically distributed. What this means is the samples are independent from one another, and the test set and train set are drawn from the same distribution. But in a sequential setting, our outputs, our predictions, affect our future inputs and observations. So the samples are correlated, not independent. And then, because our errors compound, we fly off and reach states that we've just never seen before. So our test and train distributions are also different. What this means is we can learn a policy that achieves great training error and even great validation error, but doesn't lead to good test performance. The main problem is that we have no idea how to recover. We've never collected any training data teaching us how to recover. So the intuitive solution is to do that, to use expert interaction to collect data where the learned policy goes and therefore teach the system how to recover. So in the context of this toy problem, we can do this using an iterative algorithm called Dataset Aggregation, or DAgger. Intuitively, we're using the learned policy to drive around the track. And along the way, an expert provides corrections. Then we aggregate these corrections to teach the vehicle new policies. And the first iteration starts the same way as the previous supervised learning approach. We have an expert who demonstrates a task, we sample a data set, and we train a policy. But in the next iteration, we execute the policy we've learned, and along the way, we query the expert for the appropriate corrections. And we sample a data set that's composed of images that represent the states reached by the current policy and output steering angles that are the result of querying the expert. We combine that with all our previous data, and we train a new policy. And we repeat this process again and again. And the result is that we learn a policy that drives nicely around the track. So by providing expert correction to the learned policy, by incorporating interventions, low training error actually leads to good test performance. So the previous DAgger example illustrates how expert corrections can achieve good performance in a theoretical example. But we can apply this lesson in the real world as well. For a self-driving system, interventions are a key source of learning. In this video, the vehicle stops for a pedestrian who's crossing the street to get to his car. And the human driver intervenes in order to demonstrate ideal behavior. So the purple box that shows up, and you'll see it in a second, the purple box here represents the autonomous vehicle, what the autonomous system would have done if the human driver had not intervened. And the black vehicle represents what the human driver actually did. So even though the autonomous system and the human driver both yielded for the pedestrian, the vehicle intervention allowed us to teach the system how to respond in a more human-like way. Interventions teach us when we've encountered a difficult situation and also how to recover. And interventions are also good for vehicle attention. They keep drivers engaged as they're providing corrective feedback. So there's this common misconception that a self-driving program should be targeting and measured against a low intervention rate. But in reality, low intervention rates indicate low rates of learning. At Aurora, we keep on-road testing efficient by looking for difficult situations that create high learning rates. And as our system improves, we constantly seek to expand our operating domains and environments. And here are some examples of what we've been able to achieve with our planning approach. On the video to the left, the vehicle responds safely to a cyclist cut-in. The green path represents the plan that we're actually following, and the blue path represents a contingency. And on the video to the right, we yield for pedestrians and cyclists before navigating a right-hand turn. So we've just walked through the challenges and solutions to perception and decision-making in a self-driving context. And as we conclude, I wanted to leave you with a few key lessons as we think about the future of self-driving technology. We have to fuel the rockets. We have to invest in long-term velocity over short-term gain. And we have to invest in machine learning instead of hand-tuned rules or manually engineered state machines. But machine learning is not enough. We have to combine cutting-edge machine learning with rigorous engineering to boost performance and guarantee safety. And we use interventions as learning opportunities. We accelerate progress by learning from expert human correction, and we continually seek to challenge our self-driving system. Thank you.